Our Simcoe Mountain Speaker Series. Tonight, as you know, we've got Troy Carpenter from the Goldendale Observatory. He's going to talk about eclipses and hopefully also about the observatory project. So before I hand it over to him, I just want to put a plug in for the next one, which is in February 6th, and that's going to be talking about wildlife with our local wildlife guide, Department of Fish and Wildlife guide, Todd Jacobson. And hopefully he's going to talk about living with creatures around here, like my personal favorite, the gray digger. We'll find out how to deal with the gray diggers. So you won't want to miss that if you're interested in live wildlife. Please come back to that. But without further ado, I want to introduce a fantastic asset to the city of Goldendale, and I know a lot of you are familiar with Troy and already hold him in such high esteem as I do. We're very lucky to have him around here, and I was so pleased that he said he would come and help us with this speaker series. So he's going to, without any further ado, Troy Carpenter. Thank you.
Hey, thanks for coming, everybody. I'm used to talking up. I'm used to talking up at the observatory, or now at Stonehenge. We have a building down there. And some of you, have any of you visited us at Stonehenge yet? Yeah. So we have all the gadgets there. I mean, actually, I kind of like the way it was.
You do? Okay.
Am I? Can you see me?
I can see you, but this gentleman was wondering. Okay.
So we've been down there since March of last year. It's been almost a year. I can't believe it. And why are we down there? Does anyone know?
Renovating.
Yeah. Well, renovating is putting it mildly. So most of you may have come here tonight to learn about eclipses. We'll talk about that, but let's go over the observatory project a little bit, and we can talk about some of the stuff we're doing. I have some pictures for you. So, does anyone here know why we tore down Goldendale Observatory? What'd you say?
Expand.
Yeah. Why do we need more space? Yeah, we had a good problem, which is the place is bursting at the seams with human beings. And you know, there's the amphitheater. People were always like, "Oh, there's no way you're going to fill that. You know, there's no way you'll ever use all those benches." Oh yeah. On a summer night, we'll have all the bleachers filled, if you want to call them bleachers. People standing up against the building on the sidewalk. People bringing their own lawn chairs. It's crazy. You know, people bringing their pickup trucks too close to the building without permission and sitting in the back of their trucks. It's like you do it like a sporting event or something. And it's a good problem to have, but it is a problem because we can't really cater to huge crowds like that. It runs the staff ragged. My assistants are running all over the place. We try to keep it going, but with more space, we should be able to put on a better show. But it's not just about space. We're also going to have a better equipped facility, so you'll have more stuff to do. We'll have exhibits, things to do between presentations. And on the subject of presentations, we'll have a lot more space to do those and a lot more high technology to help us do them. We also upgraded the telescope. You may have heard with a brand new mirror, and that's exciting. And it does work, and it's awesome. Not that I don't want to tease you though, but it is just
not like Hubble, is it? I hope.
So briefly, I'll show you the old floor plan. Oh, you know what? Hey, just give me 1 second. Just give me 1 second. I'm going to make this work for you so it's nice and clean. Okay, so there's the old building.
I love these pictures.
Alright, so there's the old floor plan. We all have such strong feelings about this building. We all love it so much. Unless you speak to Steve Stout, my predecessor. Was he coming?
I would have assumed he would have.
No, he doesn't want to see what I'm doing. Steve and I both agreed that the building needed to go because it had a lot of problems. So all the stick-built portion went away. Now I tell that joke because during the final night, I made this quip about how good it was, kind of a good riddance situation, and everyone was like, "Oh, how dare you!" And then Steve's like, "No, he's right. It's good riddance because the building required so much work. It would have cost more money and been more difficult to upgrade it or do an addition than to just flatten it and build a new one. So here's what we're building. So much bigger. Notice the south dome remains. That's not going away. And then the part that I'm most excited about, which might have been delayed a bit, is the rooftop deck, which is pretty cool. So, yeah. The rooftop deck allows you to see the whole sky with nothing in the way. 360. And the south dome is right there looming in front of you, so it blocks the town. So you don't see the lights from the town. So when you're up, and I know this because I would spend a lot of time on the roof of the old building, but we couldn't bring people up there because it wasn't coded for that. many other reasons. But so rooftop deck. You may have heard if you saw the newspaper announcement that the agency made a few months ago. The access to the deck, we can't afford this yet in the current phase because phase 3 ended up becoming much more expensive than we expected. That's the phase we're in now. So we expect to build the access to the roof sometime later this year, maybe the beginning of 2020. But so we may not have the roof access by the time the project is finished, but it's going to happen. The building is strong enough to support it. So notice this. It says relocated solar telescope. It's not, I don't like to call it the solar dome, but it is where we keep our solar telescope. And you might recall that smaller dome was right here, and it had to go away because it was in the footprint of the new building. So that dome's going to actually go up on the roof. Any questions about that? It's kind of neat. I will show you some pictures from construction. So here is an image right after demolition. Notice the south dome remains, but the building is conspicuously absent. That giant pile of boulders, that's just rocks that were excavated from the new foundation, which is amazing because much of that was where the old foundation was. It's crazy how many rocks are up on the hilltop. Some of you may have been Goldendale long enough to remember the original excavation where they bulldozed huge numbers of those boulders off and it created this kind of perimeter around the whole campus. So now there's even more rocks. This mountain is growing. It's no longer in that location though. They moved it over to the overflow lot. So if you want to see an amazing mountain of boulders, you can go up there and see it. So we're hoping they let us keep them because it could be useful for fill material in the future or something. Now here's a picture of the beginning of December. This is all new. This purple thing here, that's the perimeter of the new building, the new foundation. And what do you think that concrete pillar is going to be? That's the support, that's a pedestal for the new telescope, or I shouldn't say new, but the North Dome. I'm kind of excited about that, yeah. Any questions about that? As you can see, we're building a facade around the old building, the old South Dome. And that's done partly because the architect wanted some aesthetic continuity between the new and the old, but also because it protects the building. We determined this was the only valuable part of the whole park in terms of structure. It's actually brick, unlike the rest of it, which was stick built. And yet it's starting to suffer some water ingress. It's starting to have some issues. We're seeing some rusty rebar, so this is to protect that. So the building will be protected. Now this was at the beginning of December. Let me show you how much progress was made by the end of December. Look at this. So that's the new structure being built there. This is the new classroom. It's a very rainy day, as you can see. And they're putting up the supports for the siding. And here are the walls, which are going to be, they're actually being installed as we speak. I took these just, a week and a half ago, and it's already way past this. I haven't taken new pictures yet, but. Yes, that's brand new. So if you have wandered up there and violated the standoff, no personnel, no. So if you walk past the giant signs that say don't enter, you will see.
I didn't enter, Troy.
Did
It was
you enter?
a hiking trail.
That's fine.
Yeah, to see it.
And by the way, a lot of people do hike up there,
Yeah.
and the construction people do not like that, but I'm not going to tell you guys not to do it. So anyway, yeah, if you want to wander up there, you'll see something pretty impressive. It's growing very quickly. I wanted to briefly mention, this picture is not very flattering because of all the garbage bags, because they were trying to keep the water off of it, but do you see how this is kind of stepped? The whole new building goes down to the ground so that the ceiling can be higher in the classroom, because we have 3 giant 100-inch screens, and people need to be able to see over each other's heads. And the problem was, if you just do a flat room, that won't work. So we went down instead of up, and that's why they had to dig all those boulders up. So why do you think it is that we went down instead of up? What do you think? A very obvious reason. What's in there? If we built the building higher, what would happen? It would be in the way. So we wanted to make sure we retain the view shed for the South Dome. Isn't that neat? So that's why we dug down, which was expensive, but it was better than blocking the telescope. Any questions about that? Okay. No facility questions?
When's it going to be finished?
So surprisingly, the shell, like the main building, will be done in less than 2 months. But we're not going to be moving in that soon. We hope to be done we optimistically said late summer, but I'm gonna say early autumn of this year. I don't wanna say this, but it wouldn't surprise me if it went a little past that into early winter. I don't want that to happen, but we'll see. So I'm thinking this year, at some point, probably near the end, not the beginning or the middle, but we'll see. And then we wanna move in quickly, because I missed the place already. Like I said, it's been almost a year, surprisingly. And we can do a much better show there at the building, with the real equipment, so. Questions? Yeah.
A practical one.
Yeah.
You're infringing on the parking lot, so what about parking spaces?
Yeah.
So we're dramatically improving the parking lot, and that's
good.
phase 4, which picks up immediately after phase 3 finishes. Phase 4 starts as soon as that's done. Phase 4 is mostly going to be parking lot, and if you're interested to know why, a lot of the money that was allocated for phase 4 has been borrowed by phase 3 to keep phase 3 solvent, because phase 3 ended up being a lot more expensive than we expected. Sadly, because of all the delays that happened, you remember the budget freeze and the whole capital fight and all that stuff? That affected the whole state. And luckily our project survived. They laid off all the capital employees, so that was a big time waster, getting people back after they unfroze the budget. So unfortunately, waiting a whole extra year increased costs across the board, and phase 3 ended up being way more expensive than we expected. The good news is that because phase 4 did get approved, we were able to keep things moving. So as it stands, phase 4 will mostly be the parking lot. That's not very glamorous, but the parking lot is very important, I can tell you. The one that's up there now, we joke about, it couldn't be worsely designed, because based on its size and shape, you can only get like 13 cars in there. I mean, if they just made it a rectangle or not had that huge island in the middle, we could probably get at least over 20. We expect to have over parking for over 50 when we're finished, so that'll be good.
Good.
Yeah.
A second question. You said phase 3 would not allow the ramp to the roof deck for sky viewing, so how are people going to get up there?
That was supposed to be, that ramp was supposed to be phase 4, but not phase 3.
Oh.
But because phase 4 is a little bit short of money now to help phase 3 work, they're doing essentially, we're not allowed to call it phase 5, but essentially it's another ask. And if we get, depending on what answer we get on that this month or next, will determine how grandiose the access ends up being, because we have resolved to do it. We're going to find a way to get up there, but how much money we get determines how impressive that is. It might just be stairs with an elevator, because, now wait, does anyone here know why we have to do an elevator or a ramp? Does anyone know why? ADA, that's right. If we didn't have ADA requirement, we could just do steps and we'd be done, but we want to be able to get everybody up there. So that's the plan. So I've been advocating for a lift. Notice they say lift and not elevator, because elevators are very expensive and they have a lot more requirements when it comes to inspections and maintenance, but a lift, maybe. So that's my plan B. I'm going to keep telling them, listen, if we can't afford the ramp, let's do a lift, but we'll see. So I don't want to make any promises about that. So, any questions about all that? Yeah?
I noticed on that schematic that you had steps on the upper side.
Yes, and they've already been removed, and I'm like, let's put them back, let's put them back. So it's kind of a old drawing, but I'm hoping they go back. Speaking of old drawing, there is one other small change, although you guys probably won't find this very interesting. This office is very small, and this retail space is huge, and we're like, guys, we're not going to be selling huge amounts of merchandise. We don't need a huge retail space, but we do need room for staff. We could have up to 4, or maybe 4.5, half employee, 4.5 employees up there for most of the busy season. So we're going to actually grow this office down this way like that, and there's going to be much less retail space, because frankly, we don't expect a shopping mall experience at the observatory. I have this doctrine when it comes to the store, less is more. We only have a small number of items, and like we sell t-shirts, we sell tons of t-shirts, and we sell plasma globes, and we're going to sell some other little stuff, but we don't plan to have like dozens of different items. Like if you go to OMSI, they have a huge, well-stocked gift shop. We don't want to do that, so, for many reasons. So, did you have any other questions about that? All right, so I'm not going to talk too much more about the building, but if you guys do think of any questions, let me know.
What's the price tag?
Altogether, the whole project, as approved, is a little bit less than $6 million. The current phase we're on is less than $3 million, something like $2.5 million. But then that's getting supplemented with phase 4 money, so it all kind of mixes together. So, and
Yes, you said they're replacing the mirror on the 12th.
yes, I'm glad you asked. I have a picture about that.
Is it same size, bigger?
Question. So here's the old telescope. It's a little bit hard to see. This is it used to be a Cassegrain. We converted it to a Newtonian this year. Those of you who don't know what that means, the primary mirror remained the same, but we changed the secondary mirror where the focal point ends up being. This dramatically improved the telescope's contrast and versatility because it has a much more reasonable 3,000 millimeter focal length. It had a 9,000 millimeter effective focal length originally. It sounds like a downgrade. We made it shorter, but actually that 9,000 millimeters was excessive and created all sorts of problems for us. So it's much more versatile now. Now in this picture, we still had the original primary mirror built by the founders, but in this picture, we've now installed a brand new primary.
Wow.
This is part of the old focusing flange. I worked closely with a engineering firm in England to design a cell to hold the new mirror without needing to modify the existing telescope. So I didn't want to chop holes in this antique. This telescope was built in the 60s. It's the reason the place exists. So we were able to reuse every single hole in the back flange here, although they have very different function now. These are springs, and those springs pull on the cell. The cell is the thing that holds the mirror. And then these collimation bolts are actually the original bolts from the old telescope design, and they push up against the cell and they allow us to adjust it. I'm kind of proud of this because we actually managed to massively upgrade it without chopping the telescope up. So we made almost no changes to the telescope, and that was quite a challenge because for everyone's immediate solution was, oh, just drill a hole there, we'll just put something through there. I'm like, no, you don't understand, we can't mess up the telescope. And that was crazy, but we got it done. Now, yeah, and thank you, I appreciate that. And you asked about the size of the mirror. The mirror is the same size, although it's not made of glass anymore. Does anyone know what the new mirror is made out of? Plastic, that'd be a downgrade. Although you can buy plastic optics, I don't recommend it. Anyone know?
Silicon?
No, that's a good guess. Quartz. But not quartz like you dig up in a quarry, which would not be useful for optics. If you've ever seen quartz that's natural, it looks very mottled. It's fused quartz, it's fused silica. It's a synthetic product, invented by GE actually. And the actual material was not made for a telescope optic, it was intended to be a blast furnace window. And we had it made by the great Carl Zambuto, who ends up living in Washington by bizarre coincidence. If anyone doesn't know who that is, this is a true story, it's going to sound like hype. He's one of the world's best mirror makers, period. He makes research grade mirrors, although he's mostly known in the amateur astronomy community. So about that, I'm actually glad you asked because I wanted to tell a story on this subject really quickly. Some of you may have heard 2 years ago or more, we were going to have a mirror made by an outfit in Pennsylvania. There was going to be an advanced technology called cellular optics. Anyone know what happened with that? They essentially sold us a product they couldn't deliver. They couldn't do it. They kept trying to make it and they kept having all these problems. Essentially it was too thin and too weak to take a grinding. Whenever they would grind it to figure, it would bend. And by flexing, that makes it inaccurate. So you couldn't actually figure it. So we went up until right before the deadline for funding with no mirror. And it was a real crisis because we did not have a mirror because they couldn't deliver in time. And they didn't appreciate the fact that as a state agency, we do have very serious, very important deadlines. You can't go past the deadline. What happens to the money? It disappears, yeah. It gets swept, they say. So we looked at a list of possible vendors that could build us a mirror. And I contacted Carl Zambuto before I realized, wait a second, he lives in Rainier, Washington, which is bizarre. I had no idea. I had known about this guy since I was a teenager. I thought he was Italian, like I thought he lived in Italy or something, or maybe Africa. Zambuto, I had no idea. But he ends up living in Rainier, Washington. And he has a whole operation there. It's pretty impressive. And what's so incredible about this story is, he made us a mirror in less than a month. Now that's impossible. That cannot be done. The reason he was able to do it is because he worked on our mirror non-stop for 24 hours a day, 7 days a week. Either himself or a robot or his assistant were working on this mirror. And normally, he calls it a super rush job. Normally he charges you 100% premium for such a rush. He didn't charge us any premium because he was really excited to get to build a mirror for Goldendale Observatory. It's a pretty cool story, yeah. But that was nice. So Carl Zambuto is kind of the hero of that story, yeah. That's good. Yeah. And then, even more miraculously, we got through the bureaucratic red tape fast enough to get him paid, which sounds silly, but it was very difficult to get that done. That was one of the biggest hurdles, was how do we pay this vendor quickly enough, and it worked. So, yeah. So that's in there. So it's a quartz mirror, it's only 1.5 inches thick. Wow. Yeah, and that's one of the reasons you use quartz. It's much harder and stronger than glass. It also has a superior thermal expansion coefficient. That's the biggest problem with the old mirror. It's 5 inches thick, it weighs 200 pounds, and it takes 4 hours to acclimate to ambient temperature. Well, a lot of people don't know, but a telescope has to be allowed to cool down or heat up to the ambient temperature. And the more glass you have, or whatever the material is, the longer that takes. So we estimate the new mirror should cool down in less than half an hour, and that's without a fan. So pretty amazing. Questions about that? I like all these observatory questions.
Sorry about it.
No, we like it.
Well, I understand glass is really never a solid, it's just a very dense liquid.
That's actually like almost a philosophical debate. It's not technically true. It's kind of a myth. Like, for example, you hear the story about how the windows are thicker at the bottom than the top. That's not actually because of that. It has to do with the way they were actually made. It's a very popular myth, though. It is actually a crystalline solid, although it can behave like a liquid under circumstances you wouldn't expect, including pressure. Just adding pressure to it, it'll behave like a liquid. So it's not actually a very slow liquid, as you often will hear. It's not like super strong molasses or something like that. You've ever heard of pitch blende? That black material? There's a famous science experiment that's been going on for over 100 years now. You may have seen it, the pitch drop experiment, and you can watch over literally decades this pitch moving, and still that's considered a fluid. And glass is much harder than that, so to speak. So does that make sense? So, yeah. Sorry, I know no one likes to hear that though. We all like that the liquid glass story. It's right.
I tried to cut glass, older glass,
Yeah.
and it will not cut.
It's made up. They often put heavy metals into it. For example, we have some glasses at the observatory, old antique lenses that have uranium in them. We have some that have thorium in them. 10% thorium, which is an extremely dense, heavy element. So, we're going to talk now about space stuff. Not specifically buildings to look at space, but the space, outer space itself. And as you may have heard, we have a lunar eclipse this month, which is not a huge deal. Why do I say that? They're pretty frequent. They happen pretty frequently. We had one last year, January of last year. It was beautiful. By the way, those of you, did any of you come to that, by the way, at the observatory last year for the eclipse? It was wonderful. It went just great. It was early morning though, so everyone was tired. The eclipse we're about to have is at a much more convenient time. So, yeah, I'm happy about that. Yeah, right, exactly. Here's a video of the eclipse last year. This is only a few seconds of the end of the eclipse. You can see it at the end. See how the bright edge is coming? It's going to see it brighten up in a second here. See that? This is a time lapse of, I don't know, 45 minutes here. So.
Was that taken through the telescope?
Yes, not the biggest one we have. I took that through our 6-inch refractor, which is another cool telescope we have at the observatory. We actually might put that up on the roof of the new building. Those of you who don't know what I'm talking about, we have a very long 6-inch refractor. It's an F15 6-inch, and it's really good telescope. It has really good optics, and I often would use it for taking pictures. It was good for that. Now, there's a lesson here in this time lapse. It's not just to be impressed by how pretty the moon is. Do you notice how the stars seem to be moving? It was very exciting for me to take this sequence of images because I got to demonstrate the motion of the moon. You normally cannot see it in a photograph because if you properly expose the moon in your camera, what happens to the stars? They disappear because they're underexposed. Normally, if you take a picture of the moon, there's no stars, right? Have any of you ever noticed that before? And if you take a picture of the moon and there are stars, the moon looks like a supernova because you've massively overexposed it. How many of you have noticed this, tried this before? Yeah, so during a lunar eclipse, the moon is so dark that I was able to expose it properly and also get the stars. Isn't that neat? And there's a lesson here. You can see that the moon does indeed move. And of course, we all know that, but it's cool when you can actually watch it happening. How many of you have noticed the moon is in a different spot every night?
Yeah.
How does that work? The moon's orbit, right? Yeah. So the whole sky appears to go to the west. Why?
Rotation of the Earth.
Earth's rotation. But the moon appears to go to the east. Even though it sets in the west, every night it appears farther to the east. Do you all notice that? And so if it moves to the east, why does it set in the west? Essentially the Earth is outrunning it because the Earth's day is only 24 hours. And one orbit of the moon takes over 27 days. Any questions about that? Now, eclipses. We had a much more famous, much more hyped up eclipse of a different variety in August of 2017. What am I talking about? Yeah? What's the difference? That's the sun, by the way. Oh no! Oh no! What's wrong with the sun? What's happening? Dissolving? Back on this way. What's going on? No, 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 no. The moon is getting in front of the sun, right? Notice it missed there? Notice it didn't cover because we were in Goldendale, we had 98%. You know, we weren't 100%. So the difference between a lunar and solar eclipse is really in the position of the moon. So if the moon is between us and the sun, of course, we're going to have a solar eclipse. And if it's behind us, so to speak, we're going to have what kind of eclipse? Yeah, but on that subject, what's a new moon? What's a new moon?
Yeah, I always wonder why they call it new moon rather than old moon.
No.
I like that. Well, because you restart, it's a baby. So it's old right before it's new. So we say it's a very old moon when you see a waning crescent. It's an old moon. So what's a new moon, guys?
When the moon is between the Earth and the Sun.
When the moon's
Not
yeah!
on the
That's good. See what he's doing there?
ecliptic plane.
Yeah, good. So, exactly, it's off the plane of the ecliptic, and that's what we're going to talk about. Those of you who don't know what that means, we're going to go over that right now. You would think, understanding what eclipses are, and understanding moon phases, that every single time we have a new moon, we should have a solar eclipse, and every single time we have a full moon, we should have a lunar eclipse. But we don't, do we? Before I go into detail about that, anyone else want to blurt out why that is? Why we don't have eclipses every month?
Not in the same plane.
Yeah. Well, they're not usually anyway. The planes disagree with each other, right? The orbital planes are all crooked. Does anyone here know the term for how crooked an orbit is? Starts, what? No, starts with an I. Inclination. Yeah. So watch this. I'm going to put up a simulation of our solar system. And I want you to tell me if, in your opinion, this simulation is accurate or not. Blake. All right, tell me. Let's see here. Is this an accurate simulation of the solar system? What's wrong with it? So many things. There's so many things you could say that would not be
Planets
wrong.
are enormous.
Yes, planets are
And they're close
enormous.
to each other.
Yeah. Okay, so it looks like they're too close, right?
Yeah.
But it's actually the first thing you said. Their sizes are being absurdly exaggerated, right? Yeah. So let's fix that, right? Oops, wrong button. Wow, I can't do anything today. This mouse is not used to it. So let's make the sizes of the planets realistic. Oh, so disappointing. See that? Okay, so now the sizes are accurate. Now we have another problem. I noticed that the orbits are perfect circles, and that they're perfectly flat. Is that accurate? No, so let's fix that. Okay, there, now. We have accurate orbits. I'm going to zoom out. They don't look that different, right? But they are crooked. Let me zoom in especially to Mr. Mercury here. Notice Mercury's orbit. See how crooked it is compared to the other? Let me speed up time a little bit. Look at Mr. Mercury, how tilted he is. Now that Pluto's out of the planet club, Mercury has the distinction of being, again, the most inclined planet, meaning it's the most crooked. Any questions about that?
Mechanism.
What'd you say?
Why?
So Mercury, being a faster object, he experiences more orbital permutations. Over time, his precession is more obvious because he simply has more opportunities to be perturbed. And he's also quite close to the sun, and he's time traveling. How many of you know the whole story about Mercury experiencing a different rate of time passage than the rest of the planets? This is a great Newton versus Einstein story. I'm not going to spend too much on this because I want to talk about the moon thing, but just in summary, Mercury was the one planet that defied Newton because it was never quite where we predicted it to be. And no matter how good we got with our measurements and calculations, Mercury was always misbehaving. Newtonian physics predicted Mercury would be at a certain spot, and he wasn't. He was always a little bit off. Who solved it? Very famous guy, I just mentioned him. Einstein demonstrated with relativity that the passage of time is affected by speed and also proximity to heavy gravity wells, like the moon, like the sun. So Mercury is so close to the sun's gravity and moves so quickly that Mercury actually experiences immeasurably different patches of time than we do. This also contributes to his precession, which is the rotation of the entire orbit. Also, being a small planet with a relatively low mass, he's easily perturbed by other bodies. Now about that, the reason that the other planets seem to remain kind of close to the plane of the ecliptic, very important word, it's because they have enormous inertia, and so they don't get perturbed very much. This is not true of small things, like comets and asteroids and dwarf planets. So watch this, I'm going to turn on the dwarf planets, including a very famous one. Who am I talking about? Mr. Pluto. Now on this projector, actually maybe for a second we could turn the light off, if just, oh, thank you. Just because I think some people are going to have trouble seeing the red lines. So. How many of you can see red orbit lines on that screen there? There, that's what I'm thinking. Those red lines are the orbits of the dwarf planets. Now look at Pluto's orbit. Look how extremely inclined it is, and also quite eccentric as well. This is true of all the dwarf planets. Those of you who get irrationally emotional about Pluto's downgrading, I should mention this, because it makes sense. People go, oh, I get it. Pluto's been a planet my whole life. They can't change things. So Pluto fits in better with the dwarf planets, because his orbit is highly inclined and eccentric, just like them. Even though that's not part of the definition, in my opinion, that's a good argument in favor of him remaining a dwarf planet, not a planet, because his orbit is certainly far from the plane of the ecliptic, isn't it? Yeah. By the way, since you mentioned the ecliptic planes, we discovered Pluto by chance back in 1930. Clyde Tombaugh did it, because by random chance, Pluto was close to the ecliptic. He normally isn't. But they were assuming, somewhat dogmatically, that if it's a planet, it has to be on the plane of the ecliptic. So if they had been looking just a few years earlier or later, they would not have found Pluto because he was not on the plane of the ecliptic. It was a lucky chance. And now, we found thousands of objects out there, haven't we? And now we visited them. So you may have heard the big news on New Year's Day. New Horizons reached a Kuiper Belt object known as Ultima Thule. I thought it was Ultima Thule, but it's actually Ultima Thule. And that's not the official name. And that's in the whole region of the solar system, way out beyond Pluto's orbit. So those objects have orbits that are even more crazy looking. Any questions about that? Now, back to the subject. Earth's orbit, I'm going to slow this down so you don't get sick. Slow down a little bit here. There we go. That's too slow. Alright, so Earth's orbit does not look that eccentric. Eccentricity is the other word, by the way. That's how off-center it is. It also doesn't look that inclined. But it is. And Earth's orbit around the sun affects how big the sun looks in the sky. Did you know the sun grows and shrinks throughout the course of the year because we get closer and farther from it? The moon's orbit around the Earth is also crooked. It's also an inclined eccentric ellipse. So you have two crooked motions, two vectors of motion. And so because of that, as you pointed out, the chance of alignment is actually quite low. So I'm going to show you that. I'm going to put up a simulation on the screen of the sky right now. I'm going to close the solar system simulation. Before I do, are there any questions about this? Anything you were curious about while you have a 3D solar system in front of you? Okay.
Okay, this is going back.
That's
You
fine.
just said it, but I'm not getting it. Why aren't they all over the place? Why
So,
are they in the
When a star system forms, it starts out collapsing into a ball. But then, as the ball spins up, because of the conservation of angular momentum, just like what happens when a figure skater pulls in her arms, that collapsing ball turns into a disk. And this is something we can actually watch happening. For example, in the Orion Nebula, we can watch these, what we call protoplanetary disks forming before our very eyes. Because the majority of the material is in that disk, that's where the heaviest objects form. And of course, in the center of that disk is what? The star. No, we're talking about new baby star systems. So, in the center of the disk is a baby star. Baby planets form around it. Because they get the benefit of the most material, they have the most inertia. And so it's very difficult to knock something out of the plane of the ecliptic once it gets going. But billions and billions and billions and billions of comets and asteroids, and then thousands of dwarf planets, because they have much less inertia, they're more easily perturbed. Does that make sense? Yeah, and since you asked, since I have this up here, watch. I'm going to turn on some comets. Watch this. If I could stand and use a mouse at the same time. Wow. All right, so notice the 2009 P linear here. Quite eccentric. Let's look at this guy here. It looks like that's Jupiter, a planet. That's not a comet. Comet 67P. Notice how extremely eccentric its orbit is. It goes way out here and then comes in close to the sun. The tiny things in the solar system are not able to withstand perturbations by bigger bodies, and over time, they get scattered all over the place. So the sun is surrounded by these rogue objects. But the solar system is a much more peaceful place now because most of the unstable objects have been long since either tossed out, eaten by the sun, or rammed into other objects. And if you don't believe the solar system used to be a more dangerous place, just look at the surface of the moon. It is covered with craters. Because it used to be the solar system was like a shooting gallery. We had things going all over the place. So it's shaken out, so to speak, enough now. That you have less rogue or radical objects than you used to. Same thing with planet Mercury. Absolutely covered with craters. Yeah?
Earth's covered with craters too.
Earth has a handful of craters, that's right. And actually I have no, I don't have it on this computer. There's a handful of craters on Earth, but they've been erased. Why?
I said what?
Why have most of the craters on Earth been erased? Erosion. And also, not just erosion, also volcanism. We have plate tectonics, continental drift. As a result, most of the good craters on Earth are young. How many of you have seen the crater in Arizona, Meteor Crater?
Yeah.
So that's only 50,000 years old, so it hasn't had time to be erased yet. But then you have the famous crater off the Yucatan Peninsula, Chicxulub, which is often implicated in the death of the dinosaurs. That's been completely erased. You cannot see it. We discovered it with gravity maps. Now, I actually have a picture of that, so hold on just 1 second. I have so many useful pictures. Hold on. If I don't find it quickly, I'll go back on topic. Alright, so crater. Hold on 1 second, guys. Where's my players? So, here's Canyon Diablo, this is the rock from my desk. There's the one in Arizona. Yeah. By the way, if you're ever driving across the country, it's on Route 40. This is a worthy detour. It is worth the 20 or 30 minutes out of your way that it takes. This is the best crater in the world because it's so young. So, by the way, it's actually private property, and they charge you per head to get in. It's like 20 or 30 bucks. The family that owns it's actually the descendants of the guy that figured out it was actually an impact crater. And it's worth the money, it's worth it. I did that one.
Where is it?
This is in Arizona, not that far from Flagstaff. I believe it's east of Flagstaff. All right, watch this. I'm going to show you a picture of the Yucatan Peninsula. And now I'm going to show you a gravity map overlay. Do you notice that circular feature there?
Right.
Oops. The entire Earth's gravity has been mapped. We can map Earth's gravity. A lot of people think gravity is constant. It's not. If you're standing on top of a mountain, there's more material beneath you. It's heavier. Although, ironically, you're actually way less on top of the mountain because you're farther from the Earth's core. But there's technically more gravity there. So by looking at gravity maps and then comparing them with these sinkholes called cenotes or cenotes, I'm not sure how it's pronounced, we can see the rim of that crater. So that gravity map there clearly indicates a completely hidden impact crater. And when we dig down, we find enormous quantities, or I should say enormous ratios, of iridium, which is a very rare element on Earth's surface, but very common in asteroids and comets. And no matter where you go on Earth, if you dig down to that layer, you find this iridium concentration, which indicates the whole planet was covered with fallout from that event. And immediately after that, in the fossil record, what do we not see anymore? Dinosaurs. Most famously, but many other creatures also went extinct, but everyone loves dinosaurs, so yeah, so that's an interesting story, yeah.
A nice big hole up in Quebec too.
Yes, that's right. So the Manicouagan crater up in Quebec is another impact crater. That's actually much older than Chicxulub, but because it's landlocked, it hasn't been erased by the water as much, although it is filled with water. It's a lake. So Lake Manicouagan is a ring-shaped lake in Quebec, and it's actually an impact crater. Much older than that one. Yeah. That's off topic. Thank you for the tangent, though. It's a good tangent. I like this tangent.
You can see that one.
I like it. Okay, I'm going to close that, and I'm going to get back on the topic here. All right, so check it out. This is the sky right now, in this location. Now,
You're looking south?
that's right. Look, so see the S there, guys? So I'm going to turn around. So now we're looking north. Would you like to see the whole sky? I could do that. Here, watch. But that's unrealistic, isn't it? You don't have fish eyes. But if you did, if you had like giant basketball eyes, and you laid on your back, you could see the whole sky at once, right? Okay, so that's the sky right now. Now I'm going to do something here. Watch this. I'm going to turn on some lines. That yellow line, does anyone know what that is? It actually is labeled. If you're sitting close, you can read it. Does anyone know what the yellow line is? The ecliptic. What is the ecliptic? I already mentioned the word, yes.
Milky Way.
What?
Milky Way?
No, notice, actually, I'm glad you asked that. Let's go into the future a few hours, watch this. Let's go into the summertime sky. So the summer sky, the Milky Way is very obvious. Notice it has no agreement with the plane of the ecliptic.
It's a different.
No, we call it the galactic equator, actually, what you're talking about. So now I'm going to turn on Earth's equator. Watch this. That blue line is Earth's equator. We call it the celestial equator. Essentially, it's a projection of Earth's equator into the universe. If you were in, let's say, Kenya, and you look straight up, and you could see these lines, it would be right over your head. But we're up in the north, so that line appears to the south. Does that make sense? Notice that Earth's equator does not agree with this line either. Anyone know what the ecliptic is? We've already talked about it a little bit.
Plane,
What plane?
the solar plane,
Like of the solar system?
yeah.
We often say that. But I'm going to tell you literally exactly what it is. I'm going to turn off the ground. Watch this. So now the Earth is transparent. Now we can see everything. I'm going to turn off some stuff that makes this one busy. What'd you say?
I said I'll get the C-stick.
I'm going to turn on the sun. Watch. Okay, there's the sun. Notice the sun seems to be on something. The ecliptic. Yeah. To the ancient people of the world, they noticed that the sun appeared to follow this imaginary line in the sky. They thought it was the sun doing that, but what was really going on? We were orbiting it. So essentially, the ecliptic is a projection of Earth's orbit into the sky. Does that make sense? Let's speed up time a bit. Watch. We're going to walk
So we're looking through Earth, through the sun, straight out?
into space. Yes. The green line is the horizon. So when it's above it, you would see this. When it's below it, you wouldn't. I can turn the horizon off, actually. Let's do that. There. Okay, so there's the sun. Notice it seems to be creeping along. Is that actually what's happening, though? Again, it's our motion, isn't it? Let's speed up time a little more. More. Look at there goes Mercury. So, throughout the course of the year, the sky changes because of Earth's orbit around the sun. Do we all understand that? Now, what appears behind the sun is always changing. That's the stuff you can't see. So if the sun is in a constellation, you're not going to see it because it's going to be up in broad daylight, right, guys? Does anyone here know the significance of the ecliptic within the context of the zodiac signs? It's where all the zodiac signs are, because classically we call those the sun signs, which means at some point in the year, the sun is in them, right? Those of you who actually study the difference between astronomy and astrology might know that there's actually a 13th constellation that the sun moves through that's not recognized by most astrologers. Anyone know what that is? Ophiuchus, the serpent bearer, or handler. The sun actually spends more time in Ophiuchus than it does in Scorpio. Astrologers don't like that. 2,000-year-old star charts that have never been updated do not take into account the new constellation boundaries and also the precession of the equinox caused by Earth's axis wobbling. There's all these factors that seem to change, but because those old star charts were never updated, they're no longer accurate. But astronomically, the sun actually passes through 13 constellations throughout the course of a year. Or at least it appears to, because again, we go around it. Any questions about that? Now watch. The ecliptic, oh, there it is in Cancer, see that? And notice the Mercury's right there. The ecliptic is quite famous. A lot of people know about the ecliptic. But I'm going to show you a line that's much less famous. Watch this. Okay, see that kind of blue line I just drew? It's kind of a, let me turn off the equator so you don't get confused. This line is called the opposition conjunction longitude line. And this line illustrates whether or not something is at conjunction with the sun or opposition. Now, this is actually very easy to remember this because you can probably figure out what opposition is. What do you think opposition is? It's when something is opposite us from the sun. And if something's in conjunction, it's between us, right? Now, during a lunar eclipse, the moon is at opposition. Let's pretend that my head is the Earth. Here's the moon's at opposition. And during a solar eclipse, the moon is at what? Conjunction. Do we understand that? So watch this. We're gonna turn around. Watch this. So that we're looking away from the sun. Okay. Now I'm going to time travel a bit here. Let's go back to now. Okay, this is now. But turn around again. Now watch. I'm going to go back to July of this year. I'm watching the clock down here. Actually, let's see here. Let's go way over here, so we get ahead of it. November, October. Okay, it is now the end of July of this year, of last year rather. What planet do you see? How many of you recall that Mars was at opposition this summer? See that? Understand, guys, that the point where the longitude line and the ecliptic meet is exactly opposite of us and the sun. Does that make sense? So Mars was at opposition in July. Let's go back in time a few more weeks to, let's see, the end of June. And what do I see here? Oh, look at that. Moon, but also Saturn. See that? So we had a Saturn opposition in June. Let's go back in time a few more months. Watch the sky for things. Oh, look, who's that? So Jupiter was at opposition. Actually, I got it exactly there. So on the 8th of May of last year. Do we all understand what opposition is so far? Something appears behind the Earth relative to the sun. Now let's go back to that. You saw the moon there. Right there. We're going to have a lunar eclipse, right? We did not have a lunar eclipse on the 27th of June. Let me zoom in here. I always hit the wrong button. I'm going to pick on the moon here, and I'm going to show you the moon's orbit. Watch. Notice how the moon's orbit is not in agreement with the ecliptic. It needs to be, doesn't it, though? It needs to be on the ecliptic if we're going to have a what? Eclipse, right. Before I continue, are there any questions about that? Okay, watch. We're going to go into the future. We're going to find another full moon. Watch this. Another full moon. This time the moon missed below. It missed above last time. Now it's missing below. Let's go, what is that? That's July. Looks like, oh, there it is again. Now it's way off. Look at that. Let's go back one day. Still below. See that? All right, let's go to September. I got to move up again. Let me zoom out here a bit. And again, you can see the moon is missing. Again, it missed. Again, it missed. Uh-oh, 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 uh-oh. Here comes something. Here, keep watching, keep watching. Oh, oh. So on the 20th of this month, three things agree with each other. You see that? So you have the opposition conjunction longitude line, which determines if something's behind or in front of us. We have the ecliptic, which is the plane of our orbit. And the moon's orbit, by happy coincidence, happens to be right smack dab in the middle of both of them. And that's what you need to happen if you want to have a what? Yeah, but watch this. We're going to zoom in here a bit. Now, the moon's not currently in eclipse in this. I'm going to move into the future a few hours. Watch. Now, you would expect Earth's shadow to be right here, wouldn't you? You would expect that, but watch. It looks like Earth's shadow is wrong. It looks like Earth's shadow is right here. Does that make sense? What's going on there? Why is that? Explain it to me. There's a weird reason. It's not actually that weird at all, actually. It matters where you are. Your perspective matters. This is simulated for this location. Yeah. So hold on, I got a picture for you. I'm going to show you a map of everybody that gets to see this eclipse. Notice the midpoint is in Cuba. See that? If you were in Cuba, you would notice that the Earth's shadow seems to be right there, on that exact spot. Any questions about that? On that exact subject, this is very important. Some of you have probably already heard this eclipse being reported as occurring on Monday the 21st. That is incorrect for here. Specifically here, the entire eclipse occurs on Sunday the 20th because of the magic time zones. Any questions about that? So, UT is universal time. PST is what we care about here on the West Coast. Notice it's all PMs. There's no AMs there. See that? We'll look at mountain time. It starts on Sunday night and it ends Monday morning, and it gets worse the farther you go to the east. See? Any questions about that? Now, on our website, you'll see that it's reported that the eclipse actually starts at 6:30, not 7:10. That's the absolute beginning of the eclipse. These times are based on when you can actually notice it. Any questions about that? Oh, you know what? Oh, we have time.
You use what used to be Greenwich?
So, I'm glad you asked that. Greenwich Mean Time is based on Universal Time, but they are different things. Universal Time has no respect for time zones. Greenwich Time, because it is on the International Dateline, is based on UT. Now, any of you, yeah, but,
It's 5 different times.
yes, 5 different times. What do you mean?
No, there are 5 different designations for a time.
Sure. So, in science, in space science especially, we absolutely must use universal time. Imagine if we said, oh yeah, the nova occurred at 4 o'clock. Like, where? Oh, that's important at the time. Oh, AM or PM. Oh, it would be ridiculous. You can't base events on time zones, because in space it's completely meaningless, isn't it? Time zones are something that we experience on Earth's surface.
Watch time,
Watch time?
referred to as watch time.
Who refers to it as watch time? I've never heard that.
Surveyors, whenever you go out to do a celestial observation for bearing.
They use the term watch time for that?
Yeah, then you convert it to the actual time for where you are, latitude and longitude.
And you have to know the offset, right? Depending on what.
You have to do the equation of time.
Right, and the equation of time is very complex, and it's something that has become a lot easier now because we have devices that do it automatically, and it
Do
makes
it
us
on
very.
your phone now.
Yes, and it makes us very lazy, because you can fill a whole page doing the equation of time. And that matters a lot in astronomy, because it's just like you said with surveyors, if they care about the position of an object in the sky to help them determine position, its position will appear to shift because of that pesky Earth rotating, right? So that's why we have to come up with a standard time that's not affected by Earth's motion. And by the way, did you know that we update universal time frequently because of things like earthquakes causing actual subduction of mass of Earth's surface, which means Earth actually spins faster? The day gets a little shorter, and we're talking about an incredibly tiny amount. But over time, that small deviation adds up. So they frequently update universal time to compensate for these variables. Earth's rotation rate is not a set constant. I think that's kind of neat. And so when you do the equation of time, of course, you're going to be using it based on the most up-to-date time standard, not some recorded one. And what kind of clocks do we keep that on, by the way? What kind of clocks? Atomic clocks, right. I didn't want to spend too much on this boring screen with times on it, but any other questions about that? So I just want to remind you, if you have friends in other time zones, this gets a little more tricky for them. But for us here on the West Coast, we're lucky in that this entire eclipse happens not only on the same day, but at a very convenient time. This isn't that late. Like I said, the one we had last year was up in the early morning. Yeah. So, any questions about that? Now, there were some terms there. We see penumbra here. What the heck is penumbra? Yeah, it's, so umbra is Greek for, I think it's Greek, not Latin, is Greek for shadow, and penumbra means almost shadow. So I'm going to show you a visual representation of that. Okay, this is a simulation of the eclipse this month. Do you see that we have 2 circles here? We have this kind of dim circle, and then we have this brighter circle. This is the penumbra, and this is the umbra. So what? Oh no. See what's happening? That's, I don't like that. That's simulation sheets that make the moon look like it's getting brighter, but it doesn't. I don't like that. But I wanted to show you the 2 different zones. Let me show you a better, since you noticed that about the brightness, let me show you a better picture. Here's another simulation. Notice the moon is not actually moving through the center of Earth's shadow, it's actually missing to the north. But because the moon is 1/4 the size of the Earth, it doesn't have to be exactly centered. This is not true of solar eclipses, is it? Because the moon and the sun appear similar, although not exact, that's a popular myth, but because they appear similar in the sky, the alignment is much more critical if you want to have a total eclipse of the sun. But on lunar eclipses, you can get away with a lot because Earth's shadow is so much bigger than the moon. Any questions about that? Now, I haven't heard the question yet. Maybe it's because you already know the answer already. Are any of you puzzled about the color change? You know, famously, the moon turns orange or red. Why? How come? What's going on there?
Lightning runs around here.
Good. These are 3 different pictures we took at the observatory of different eclipses. This is the eclipse, when was this? This was April 4th of 2015. Here's an eclipse. This was October 8th of 2014. And then here's the eclipse we had last year. I wasn't very scientific about when those pictures were taken, so they're all different parts of the eclipse. But notice here in this image, we can see that the moon is moving back into the light, because this is the end of the eclipse. But those colors are important. Now, I heard the right answer. Who said atmosphere? What about the atmosphere?
Well, the distortion of the
Yes. Distortion.
the density.
Refraction, red light refracts more.
And
Well, less actually. Let's go over that. This is interesting.
it acts like a lens.
Kind of.
Like a prism of light.
So I'm hearing the word refraction, and you said the word lens. That has to do with bending light. But we're also talking about diffraction, which has to do with scattering light. Air molecules scatter different wavelengths preferentially. So higher energy wavelengths like blue or violet get scattered every which way, which is why we have a blue sky. But lower energy wavelengths like orange, yellow, red, you know, like do it backwards, yellow, orange, red, those are scattered less. So when you're looking straight at an object through the air, it appears biased towards the red. And by the way, that's why you have a pretty red sunset, because you're looking through more air. When the sun is low, you're looking through like 1,000 miles of air. But when the sun's like straight up, it's like 200 miles of air. This exact same thing happens to the shadow of the Earth on the moon. Yes?
An interesting phenomenon that most people have never really paid attention to is when you're flying in an airplane, look at the shadow on the Earth. At the right altitude, it will act like a lens. It'll be very bright.
It's called a glory. Yeah.
And it'll either be, depending on how high you are, it'll be light or dark.
You, believe it or not, you don't actually have to do that in the airplane. Have any of you ever seen, like, you're looking at a stand of, let's say, wheat, and it seems like there's a halo of brightness near the center of where you're looking? It's a similar phenomenon to that. It has to do with being coaxial to the rays of light.
Yeah, because the air gets compressed by the plane as it goes through it.
That's part of the reason, that's right. But it also has to do with your perspective being collinear with the rays of light as opposed to looking off to the side. But that's, so how many of you have noticed that before? That brightening below the plane. That's a cool effect. So watch this. If you were actually on the surface of the moon during a lunar eclipse, the Earth would look very frightening. The Earth would look like a giant red ring. Do you see that? What you're experiencing is a global sunset. You're seeing all the sunsets in the world at once. And that's bathing the moon in red light. That's why that's why the moon turns red during an eclipse. Any questions about that?
Say that again.
So, if you were standing on the moon, ignore the rainbows. Those are there for, I actually don't find those to be very helpful in this picture. The Earth would look like that right image during the moment of the deepest eclipse, because you're seeing sunlight filtering through the Earth's atmosphere. The red rays of light are allowed to proceed in a somewhat linear fashion, where the blue and the violet are scattering all over the place in outer space. Does that make sense? You can see that happening here. Now look at this picture. This was the April picture I took. Not only do you see the red deep core of the shadow, but do you notice this blue fringe? That's actually there for 2 reasons. It's partly because of what I just described, the blue being scattered, but it's also because of ozone. They can actually study Earth's ozone layer by looking at the color of a lunar eclipse. It's actually useful for science. A lot of people don't know that. During a lunar eclipse, they actually perform real science by studying the color of the Earth's shadow. Isn't that neat? Any questions about that? Now, we are out of time, but I'm not going to just end the show right now. I just want to let you know. This was kind of more random than I expected. We spent about the first half of the show talking about all kinds of stuff, which is actually fine. But I think we should, let me ask permission first. Do we have to all clear out, like, is the room turning black?
No, but we should give people a chance to
Yes.
leave if they want.
So if you don't have questions, or if you don't have anything new to add, and you have to leave, I won't be offended. But if any of you want to stick around, I'm not itching to get out, so I like answering questions, and I do have more material I didn't get to show you. So,
Sky tonight anyway.
what is it? Yeah, it's cloudy, that's right. So, all right, well, anyway, those of you who do have to leave, thank you for coming. I hope you had fun. I hope you learned something tonight. I hope it was worth your while. So, it looks like no one's leaving, that's nice. Okay. So, all right, so let's move a little faster, just so I don't keep you here all night. Is there food? Oh, I didn't notice that. I see people munching. I should have ate some.
Sure.
I've talked about a whole bunch of different stuff tonight so far, so I bet it's perhaps piqued your interest somehow? Any questions that have popped up if you haven't asked yet, anything? Colin? Yeah.
On the solar eclipse, when the previous screen where you showed the flares of light.
Oh, yeah.
I vaguely remember something that we were supposed to watch for the solar eclipse, something about a flame of light or.
A prominence? Well, during a,
Am I hallucinating?
no, not a flame. Let me show you a picture of an annular eclipse. Now, does anyone know what an annular eclipse is? Yeah, that's it, right. But you know why that happens? Do you notice how the moon is unable to cover the sun? This is because of something we already talked about tonight.
Our distance to the moon.
Right. Earth's distance from the sun is always changing because of our elliptical and also eccentric orbit. Sometimes the sun appears bigger and sometimes it appears smaller. Same with the moon, because of its eccentric and elliptical orbit. Sometimes it appears bigger and smaller. Sometimes if you have a combination of both extremes, the sun being close and the moon being far, the moon cannot cover the sun, and we call it an annular eclipse. Sometimes the opposite occurs, the moon looks significantly bigger than the sun, and you get an unusually long eclipse. For example, the eclipse that we had in August 2017 that was so famous, that was only about 2 minutes and 40 seconds. But it's possible to have a solar eclipse well over 7 minutes. It's because of that size change. And this is what I was talking about earlier, when you hear that thing about they're exactly the same size, it's not true. And they can change quite a bit, as you can see. Now, the reason I brought this picture up, notice this thing shooting out here? And those are called prominences. And those are not fire or flames. The sun is not burning. The sun is not on fire. Those are electromagnetic phenomena. Enormous columns of hydrogen and helium plasma trapped in magnetic fields. Normally you cannot see them safely without very expensive and complex solar filters. But during a solar eclipse, it's possible to take pictures of these with normal equipment. Now that's kind of dishonest, because this picture was taken using those special filters, because it was not actually a total eclipse, it was an annular eclipse. But during a true total solar eclipse, you can take pictures of those without filters. Any questions about that? And to hype up what we can do at the observatory, watch this. We have a really nice solar filter, as you know, as part of our upgrade. Phase 2 of the upgrade, we got a nice solar telescope, and we have modified it a bit. So check this out. This is 2.5 hours of time lapse in 18 seconds. Look at the motion of that prominence. Isn't that neat? Because the sun is so far away, because these structures are so enormous, you have to do time lapse to reveal their motion. Just so you know, the Earth would easily fit under that arch. So this is a truly immense structure. Yeah. Earth would be a small dot at this scale. So again, this is about 2.5 hours and 18 seconds. And that's the kind of thing you can see during a solar eclipse without the high-tech filters that we use to take these images. Any questions about that? I got some other stuff. Let's see. Look at that. See the motion of that material? That's unrelated. Let's see. Here's another one. This one's less impressive, but you'll notice some motion up here. See the movement there? Yeah. So you have a nice little prominence there.
What's the difference between a prominence and a solar?
Solar flares or explosions. Prominences, and by the way, that's the planet Mercury, that little dot. We had a Mercury transit in 2016. We have another one coming up in November of this year. I hope we'll have our solar telescope running for that. So solar flares. I didn't know that sound. I gotta mute that, as I was saying. So solar flares are explosions on the sun. People often see stuff like this and think it's a flare, but it's actually a prominence if you're talking about. These are relatively peaceful structures that will exist for a few hours, days, weeks, sometimes months, never years. And the reason they're so temporary is because the magnetic fields that create them are highly unstable. Which leads us up to a whole other tangent, but this is a worthy tangent. Watch this. You mentioned the corona earlier of the sun. Now this, before you all go, oh no, I did not take this. This is not a picture. This is a simulation made by a computer of what the corona of the sun would look like on eclipse day in 2017. Let's see if it was accurate. Watch. That map tells us what it should have been. Watch. That's a real picture. This is the prediction. They were pretty close to correct, weren't they? And the reason it was possible is because of that map I just showed you. This is a map of the sun's magnetic field.
Whoa.
We can do that now. This is new technology. This is brand new. You couldn't do this just a few years ago. So now you live in the future. We have the ability to map the sun's magnetic field. And all these lines of flux are all extremely unstable, and they will fail within, like I said, minutes, hours, days, weeks, sometimes months.
What are the different colors represent?
Different lines of flux. The sun does not have a single north and south pole. It has millions of north and south poles. And the different colors allow you to differentiate the different lines of flux. Again, this is very futuristic science. We didn't have this just a few years ago, so we live in the future. I tell the young people, they have no idea how lucky they are. We've learned so much. And not only have we learned a lot, we have the ability to disseminate that knowledge very quickly, don't we? And for free, or cheap. Kids don't pay this phone bill, so it's free for them. Oh, I can learn everything. Yes, it's for free. Questions about that? I can make it better. It's going to be kind of bright. Watch. It moves. I'm going to stop blinding you. We go back to something that's not bright. So there's a picture that's not bright. That was a good tangent. Any other questions about that stuff we just talked about? This is a good group. I appreciate all these questions, by the way. It's good stuff. Now, let's briefly, just to finish the topic at hand, talk about the eclipse. Are there any questions specifically about this month's eclipse? You may have heard all kinds of crazy hype about it being a super wolf moon. What is that? What is all that? Anyone know what the super means?
How close it is to Earth.
Very good. Check it out. You're going to like this. This is a cool picture. Before you get confused by this image, this is a composite image. These are two images of the moon composited on top of each other. And what do you obviously notice? Because of what we were talking about earlier, because of the moon's inclined eccentric elliptical orbit, sometimes it's close and we get the big one. Sometimes it's far, we get the little one. If the moon is full, when it's little, the made-up term for that is micromoon. And if it's full when it's close, we call that a what? We just said it. A supermoon. So the eclipse we have this month is a super moon wolf eclipse. Trademark. Yeah, so, no. That's all nonsense. Just so you know, astronomers do not recognize the terms micromoon and supermoon, but they are useful. The reason astronomers don't recognize them is because they're not precise definitions, because if you wanted to be really precise about it, say that it has to happen at the exact millisecond that both converge, then you would never see one in your whole lifetime. So there's some gray area around how many hours into the perigee or apogee you have to be to have the, let's see, super or micromoon, respectively. Any questions about that? Perigee is when it's closest, and apogee is when it's farthest. By the way, when it comes to Earth and the Sun, when we're closest to the Sun, we call that perihelion, and when we're farthest, we call that aphelion. Helios, sun god.
Where in the sky will the moon be for this?
Oh, good question. So this is a very convenient eclipse because the moon will have risen before it starts, and it'll be about halfway across the sky by the time it's over. The moon will rise in the east, and about an hour after that, it'll start to eclipse. So to answer your question, the moon will be in the east at the beginning of the eclipse. Now, I could keep just talking, or I can show you. Watch. So let's turn on the horizon and the ground. Okay, let's turn the cardinal points back on. See the east there? Let's go back in time a few hours. Now, zoom in. Oops, wrong time. So the green line is the horizon. So the moon has just risen. And it starts to eclipse. Let's see what time it is. It's 6:30. There it comes. Here comes the shadow. So at maximum eclipse, the moon will still be kind of halfway between the east and its highest point in the south. So right about there for maximum eclipse. That's a good spot for imaging in, so that's good for taking pictures. Those of you who are trying to photograph this event, the moon's going to be well placed. Well, of course, there is one very serious wild card. What? Weather, yes. Now, I don't want to jinx it, but last year we got really lucky. It was great. I showed you the pictures I took of the one last year, so we were able to, it wasn't completely clear, but it was clear enough that we were able to see it. Now here's the good news. I have a little pep talk for you guys. If it's cloudy, don't get aggravated and just give up and go to bed, because lunar eclipses take hours to finish. It's like a 5-hour event, 5 hours. In that time, there's going to be many opportunities where the clouds might move away. So even though it might not be crystal clear, you'll probably get a few chances to see the eclipse. Any questions about that?
Good to know.
Yeah, so stay optimistic. And even if the weather, I'll tell you from experience, I've been at the observatory for almost 6 years now. Even on nights where it's awful, like overcast, you'll get these little sucker holes that'll kind of appear, you know. So you get a few minutes. So as long as just being able to see the moon in eclipse for a few minutes is nice. So don't give up. That's advice. This happens a lot. People just won't even come because they think it's cloudy. So just be aware of that. Yes?
Will you be doing anything at Stonehenge
Yes.
that night?
So the good news is, because of the convenient time of this, it doesn't require us to do anything special in terms of our normal operating schedule. We are open on Sundays. Our show starts at 6 as usual. The difference is, instead of closing at 9, which we do this time of year, we're going to close at midnight. Because the eclipse is over by about that time. It's 11:50. So we're going to be open from 6, that's not 6 hours. That's a long night for me. So we're going to be open from 6 to midnight.
6 hours.
Yeah. And keep that in mind. I will say, as you saw in that time chart, it doesn't really get going well until you notice it, until 7:10. So just be aware. I normally don't encourage people to show up late, but for such a long event, I wouldn't hold it against you. But you do get these diehard fans who will come at 6 and stay the whole thing. I mean, we get that. People do that for all kinds of like meteor showers. People will stay for the entire night. But you don't have to. I won't be offended if you have to come later or leave early. Some people will show up like right here at the best part. And that's okay. Sorry. Now we will have telescopes set up, of course. So, or telescope singular, we'll see. So, if you're wondering, even though the big scope is still up at the observatory, we do have nice telescopes down at Stonehenge. How many? I forgot. I think I asked earlier. Have any of you been down for the show? Did we use 2 telescopes the night you were there? Or
No, just one.
just the one big one? Okay, yeah. So we have a big 14-inch Newtonian. We have a 7-inch Maxitov Cassegrain, and those are really good telescopes. And so, especially for eclipses, it'll be nice. Again, hoping that the clouds refrain. So we'll see. Questions?
Do lunar eclipses occur in a regular, repeating,
Good question.
predictable manner?
So, I like to use this very strange analogy. How many of you have been sitting in line in traffic and noticed that your turn signals occasionally synchronize? You ever noticed that before? Your turn signals all blink at different rates because of the electrical eccentricities of your wiring in that car and the little relay. And yet, occasionally, your blinker will seem to synchronize with the blinker of the truck in front of you. And then you'll watch it and it kind of goes out of sync. But then if you watch it long enough, it'll do it again. If you have 2 systems that oscillate at different frequencies, they will occasionally overlap because of the rule of averages. So, in the case of lunar eclipses, we call those Soros cycles. And there's hundreds of them. We know this now because math, supercomputers, have allowed us to look deep into the past and deep into the future and determine what cycle a certain particular lunar eclipse is on. Now, I admit I forgot to look up what cycle this is on, but you can Google that very easily. If you go to the Wikipedia page for this particular eclipse, it'll tell you what Soros cycle we're on. And so, the neat thing about these cycles is they can last for centuries, and they're also not permanent. They come and go. And the reason these cycles are not forever is because all these variables shift. Did you know Earth's distance from the sun is always increasing very slightly? The moon's distance from Earth is also increasing. Did you know we're losing the moon about 2 inches a year? Also, the orbit of Earth precesses. The orbit of the moon precesses. And because of that, none of these cycles remain permanent. That's a good question. Eventually, in the distant future, it will be impossible to have these eclipses, both lunar and solar. Yes?
Also, you have the 3-body problem.
Yes. Then you have these other bodies that are perturbing the Earth and the Moon. The 3-body problem, or the better term is the many-body problem. We live in a universe with many bodies, and they're all tugging on each other. And it wasn't until supercomputers that we could start really tackling the many-body problem because there are so many variables. So you have the tiny perturbation of the planet Venus tugging on the Moon and the Earth. Now, it's like almost nothing, but over millions of years, it adds up to something. So, and this is why, like I mentioned earlier, the comets and asteroids are also crazy, because they're being perturbed by many bodies for billions of years. So none of these cycles are permanent. That's a good question. Anything else on that? Any follow-ups on that? That's a good one. I like that. That's good. So
what's going to happen to our axial tilt when we lose the moon?
So you've probably heard that without the moon, Earth's axis would precess more rapidly. Right now it takes 26,000 years for Earth's axis to precess once. Now, since you asked that, when I have the software up, I want to show you something that you guys might find kind of cool. What's the most famous star in the north? And what's the deal with the North Star, Polaris? Is there something special about it? No. It's all about Earth. and the fact that our axis roughly points towards it. Notice I say roughly. This is the North Celestial Pole. Notice that Polaris is not actually in it, but it's close enough that it doesn't move very much. But we have a time machine here, so we're going to go into the future. Watch. Okay, it's now the year 2025. Let's go faster. It's now the year 3000.
Whoa.
Hey, where'd Polaris go?
Whoa.
It's way down there. See that? Watch this. Let's keep going into the future. Watch this. Something cool happens in the year 14,000. I know this. I have seen the future. All right, so look, in the year 14,000, we have Vega as the North Star. Vega is a much brighter North Star than the North Star. How many of you have heard the ridiculous myth that the North Star is the brightest star in the sky? I get so angry about that myth. Because it's so obviously false. Because the North Star is not bright. It's not even the 50th brightest star. But it's famous because it's useful for navigation. Today. Now I like to tell this story in the context of Stonehenge because, as you know, the real Stonehenge in England might have been some kind of celestial calendar. But it was built 5,000 years ago. Why is that a problem? Because Earth's axis has wobbled that much. So even if it was actually a calendar at that time, it would not be useful today. I bring this up because it's known that they tried to copy the alignment of the real Stonehenge with the Mariel Stonehenge. They did not quite succeed, but frankly it wouldn't have mattered if they had succeeded because of what we're talking about. Unless they waited 21,000 years from now, which is a long time. That won't be there anymore. So to answer your question, the axial precession of Earth will dramatically increase in speed. Now, it probably won't end the world, but it would certainly cause the seasons to change over geologically brief periods of time, over maybe hundreds of thousands of years versus millions or billions of years. So it would certainly affect life on Earth, but it probably wouldn't end the world. I've heard many people say, oh, if it wasn't the moon, the Earth, all life would perish. No, but it would be challenging though. The good news is you don't have to worry about that. Because, no, seriously, here's why you don't have to worry about it. We're losing the moon so slowly, the sun will die before we lose the moon. Oh, okay.
How reassuring.
Yes, how reassuring that all life will be extinguished long before we have to worry about all life being extinguished. By the way, does anyone here know how long the sun has left? We have a pretty good handle on that now. About 5 billion years left with a B. And we have about 1 billion years of its current luminosity. So we've got about 1,000 million years to live. That's a long time.
So we're gonna have to move?
I tell the young people, like, it's their job to invent warp drive or hyperdrive or stargates, and then we can watch it from a distance. But that's so far in the future, we won't be human anymore. We'll be like clouds of energy or floating robots or something.
Dinosaurs.
So we're not here. So yeah. Anyway, please don't worry about the moon leaving. Now, it sounds like a joke, but I will tell you, this is a true story. At the observatory, when we do our solar show, we talk about the sun's life cycle and the other stars' life cycle. And this fills people with anxiety. People are like, the sun's going to die? And I'll be like, in 5 billion years. I'm like, that's 5,000 million years. Don't worry, you have much more immediate concerns than the death of the sun. Trust me. And like you said, we'll be long gone watching it from a distance. Yeah, so as long as the young people save us with their technology and their warp drives. So, yeah. Any questions about all that hilarious, real stuff? It's all very important, So, well, I'm going to start wrapping it up. Let's do like 2 more questions. Can we do that? Anything else? Anything totally unrelated to all this? I did want to, who set up the nice model? Who was that set up the? So I want to point that out really quick. There's another reason why eclipses don't happen very often, and it's very simple. Show them. So there's a little ball up there on the upper right. That is a scale model of the moon, scaled to that Earth globe over there on the table. And she has taken the time to correctly distance them.
Wow.
So the moon is actually quite far from the sun. Wow, from the Earth. The moon is actually quite far from the Earth. And that's yet another reason why it's so unlikely for our paths to cross. And I have a drawing here for that. Watch. See? Any questions about that? You know, the moon's not that far away in a cosmic sense. In fact, it's essentially on top of it. You could drive to the moon.
How long did you say it would take to drive to the moon?
Yeah, we figured it out, so it wasn't even a year. We can do the math. Watch, it'll only take a second. Watch. Watch this. Windows calculator.
How fast are we going?
All right, so, okay, so we're going to drive at the speed of a normal car. So let's go 70 miles an hour, right?
there isn't traffic, at least today.
Okay, so that's 3,429 hours, divide that by 24. You could get to the moon in only 143 days, assuming you had traction in space and unlimited food, water, air, radiation shielding, etc. Yeah, but think about that. At a speed of only 70 miles an hour, you could get there in less than half a year. I think that's kind of impressive. What about the sun, though? How far away is the sun? You should all know that.
93 million miles.
93 million miles. Watch this. Same exact map. We're going to drive to the sun at a blistering speed of 70 miles per hour. That's 1.3 million hours, by the way. Oh dear. Divided by 24. 55,000 days. Oh dear. Want to predict before I hit enter? How long is it going to take us to get to the sun?
Long time.
152 years. That's how long it takes to drive one astronomical union, which is the average distance between Earth and Sun, 1 AU. At 70 miles an hour. It takes you 152 years to get there. Any questions about that? Yeah.
Actually, you get there a lot faster than that because gravity will start sucking you in.
No, so to make this easy, we're pretending Magic Space Car is going 70 miles an hour. That's how fast it's going. And the reason we say, you know why I do that? Because you can visualize it.
Yeah.
You can imagine going 70 miles an hour. Right. Now, how long did it take the Apollo astronauts to get to the moon? 4 days. Why? Were they going 70 miles an hour?
No,
No.
not quite.
They were going well over 2,000 miles an hour once they had left the translunar position. And so that, it only took them, like I said, less than 4 days to get there. Their entire mission was like 8 days. It's pretty quick. Because they were in a vehicle that was powered by a rocket. Not just any rocket, by the way. The Saturn V is famously the most powerful machine ever made by humans. Unless you count the Russian N-1, except that it kept blowing up. So that was their moon rocket that never managed to actually make it to space. But if it had, that would have been the world's most powerful rocket, but it never made it to space. So the Saturn V was the most powerful, successful machine. And by the way, it's appropriate to end the show on the Apollo program. Why? Yeah, so we're on the 50th anniversary of the first human to leave the Earth, Apollo 8. Yeah, so hang on, I got something for you. Just give me 1 second. I made a little thing about this. It'll take me 1 second. Yeah, let's talk about the moon hoaxers for a second. So, the moon hoaxers, the people that think we didn't go to the moon. These are images of the landing sites. Enough! I don't think any of you are crazy, but if you have any crazy friends, show them this picture. This is a real picture. These are the 6 landing sites. And here's where they all are. Here's the dates. This is a nice picture. I like this. I just got this today. So, look at the dates. 69 July was when we first landed on the moon. But they went to the moon, but didn't land on Apollo 8 several months before that. So we're coming up on the 50th anniversary. So, any questions about that? Who's missed? Yeah, they were. Isn't that amazing that the speed? It's because they had the money to do it. They got the funny. Let's do it. Let's keep the rocket fueled. That's actually the sad story about Apollo 18. It was paid for to be fueled, and then Nixon killed it because of political reasons. But there should have been Apollo 18. It was funded, but they ended up using that Saturn V to launch Skylab. Remember Skylab? So, anyone remember Skylab? So the final Saturn V launch was actually to launch Skylab as opposed to Apollo 18. So, anyway, who's missing here? What happened? That's an amazing story. In some ways, that story is more amazing than some of the successful stories because those guys made it back. They should not have made it back. That was quite a story. It's an amazing story. A random thing. I use Quora a lot. It's a question-answer website, and quite often you'll get comments from real NASA employees. And I saw a cool one about that movie Apollo 13. If any of you have ever seen it, he said it was the most accurate science movie he'd ever seen. So if you ever watch Apollo 13, that's not heavily dramatized. It really is a true story, and there's not much. They didn't really add much fluff to it. It's a real film. So if you want to kind of get an idea of what happened, Apollo 13. Although I read the book, I can tell you it was even worse than the movie depicted. It was a horrible experience for those guys, and yet they made it back. So quite a story. So anyway, that's a nice thing to have to show. And just imagine the hunks of material they left behind will see that lunar eclipse at the end of the month, or the 20th. Question?
I have a gravity assist question.
Oh wait, he's been
Go
very
ahead.
patient. Go ahead.
I have an unrelated question to a lot of this.
Sure.
About the International Space Station.
Yeah.
We like to keep track of when it appears in our area. And I wanted to know the reasons behind the variabilities in time and
Sure.
position.
Hang on, I can give you that. I do actually have something for that. Just give me 1 second. So, how many of you have noticed that the International Space Station never seems to go over at the same time? Yeah. So, if you were to lay on your back on the Earth's equator and look straight up, you'd see all these geosynchronous satellites that seem to wander up and down because they're being perturbed by the moon's gravity. They've lost the ability to maintain their positions. Where the geosynchronous satellites don't seem to move very much. And that's because they're being maintained in a position over Earth's equator. That's not the nature of the orbit of the ISS. The ISS is deliberately heavily inclined in respect to Earth's equator. And for a beautiful humanitarian reason. Does anyone here know one of the reasons why the orbit of the International Space Station is so deliberately crooked?
To stay away from the debris.
No, it's a nice thing. What?
So we can see all
Who
the,
sees it?
all the people that are.
Everybody.
Yeah.
There's not a single place on Earth, not one place you can go where you don't get to see the International Space Station. Now, the reason you don't see it in the same spot every night is because their orbit is only 90 minutes, where Earth's day is 24 hours, and we rotate beneath their orbit and there's no synchronization there. Does that make sense? Yeah. Now, if they were out there in the geosynchronous belt 26,000 miles up, then they'd always be in one spot. But that's very dangerous for them. Does anyone here know why we don't live out there 26,000 miles up?
All the junk.
No, actually, it's way safer out there for that reason. That's funny you say that. It's actually much more safe way up in geosynchronous.
It's the radiation.
Radiation, that's right. Because they're so far from the Earth, they're not protected.
Yeah.
So, let me show you something, guys. This is pretty important. Something we don't often learn
And
about.
your geosynchronous satellites are not stationary. They move.
Of course, they move. But
And
it takes
they're in a controlled orbit.
That's exactly right. Here's one of the astronauts on the space station. I got, oops, hang on. That's the accurate thing. Hold that thought. So, I want to show you something. Here's back when the space shuttle was still flying. Look how close they are to the Earth. They're only 251 miles up. At that altitude, they're protected by the Earth just by physically being there. The Earth is like a giant umbrella, protecting them from radiation. And they're well underneath something else. What are they under? They're beneath the Van Allen belts, which are the thickest parts of Earth's magnetic field. So they're protected by Earth's magnetic field above, and the Earth itself below. That's right. If they were to live out there at the geosynchronous belt, they actually would not be at the Van Allen belts, but they'd be receiving immensely more radiation. And by the way, radiation is the problem. It is the hazard of space travel. We see a lot of science fiction movies. They deal with food and water and comfort. Oh, I need to get around. I need to run on the treadmill. I need to watch TV. The biggest concern is radiation, period. We don't appreciate the danger because almost all of human spaceflight has occurred at this altitude. Almost 100% of human spaceflight has occurred at LEO, low Earth orbit. The only missions that allowed humans to leave were which ones?
The moon.
The Apollo program. Yeah, so the Apollo program, and that's actually, I think, one of the most significant things about Apollo. A lot of people don't realize it. The Apollo program was the only mission series in human history where people left low Earth orbit. All other manned spaceflight happens right there. Isn't that amazing? It's almost disappointing, isn't it? We haven't gone very far, have we?
No.
That's because space is dangerous. Now, what's wrong with this picture? There you go, that's better. So, that's the way they're pointing. Did you know most of the cool pictures we see from the space station were taken with handheld SLRs? Isn't that funny? You would think it would be like covered with cameras. The problem is, putting them outdoors, they'd be destroyed by radiation. Don't imagine that. So, by letting people just use portable cameras, first of all, it's a lot cheaper, but also it's protected.
How did the Apollo people protect themselves from radiation?
It's a beautiful question. This is I like this picture. To answer your question, the reason the Apollo astronauts survived is partly ignorance. We didn't realize how dangerous it was. And also, they were there for only 8 days. And here's the scary part about that. Even though they were only up in space for a little over a week, they experienced statistically elevated incidences of various health problems that may be linked to radiation exposure. Because again, at the time, we were ignorant to that hazard. We can't prove that, but there seems to be a higher incidence of like heart disease, vision problems, brain issues with Apollo astronauts, right? By ratio. Now people say that's because of their lifestyle. they were living like kings. Well, maybe, but I think it's a good chance because of the radiation. There's a lot of evidence for that. So we haven't proven it, but we don't really have to prove it because astronauts that do and cosmonauts that do work on the ISS do experience health issues that are definitely linked to radiation exposure because they don't spend a week up there, do they? What do? Months, and then you remember Mr. Kelly was up there for a year? Yeah. There's been a few cosmonauts that went beyond that, yeah. So, you are worse for wear when you come back from outer space, not just because of the effects of microgravity, but also radiation. Have you ever heard the stories about they close their eyes and they can see flashes of light? That's cosmic rays hitting the molecules in their eyeballs. It's kind of scary. Yeah. And I gotta say, I don't want to be a wet blanket, but when I was a kid, every kid wants to go to space. Now that I know a lot about space, I like the Earth. It's very safe here. It's a wonderful place. Yes. And look, she's admiring it. She wants to go back. Exactly. Oh, by the way, this is their safety box. Whenever, this is unrelated, but whenever some space junk comes within this box, they have to go into their safe room to protect themselves in case the collision happens. A lot of people don't know. This is an unrelated picture. A lot of people don't know the space station does get hit by stuff. It's a problem.
A lot.
You mentioned the space junk. They're in much greater danger than something much higher, because that's where most of the stuff is, in low Earth orbit. And I promise, this is the last thing I'm going to do. This is the last thing. This is the last thing. Because I want to show you this. Those of you who have not seen this might be freaked out by this. What are all these green dots?
Satellites.
Specifically, yeah, it's a lot, isn't it? You're like, wow, there's a lot of stuff orbiting the Earth, you think? Until you add in all of the inactive satellites. Let's do that real quick. Oh my goodness, what have we done? Wow. Oh no! Humans have found a way to pollute space. And this is a real
It's our
problem.
shield.
What?
It's our shield, nobody can get
Our
it.
shield that we're protected. We need to add more. Eventually we'll be safe from the aliens. This is a very realistic solution. Yes. So, just so you guys know, before you get really freaked out, these dots are obviously expanded in size so you can see them. They're not that big. These are like the size of cities. But Earth is indeed surrounded by space junk. And this is a real problem because that material is not moving very slowly. Does anyone know the speed of the low Earth orbit objects? 17,000 miles per hour. That's not a joke, 17,000 miles per hour. Notice how much slower the geosynchronous satellites are. They don't have to go as fast because they're so high. Yes?
Those satellites are 2.5 degrees apart.
They're supposed to be. You're talking about the ones in the geosynchronous?
Yeah.
That's right. And I say they're supposed to be because once they run out of fuel, they start to wander. A lot of people don't know, the FCC and organizations like it in other countries regulate the spacing. It's very much like real estate, but it's not done because of territory, it's because you don't want the satellites to interfere with each other.
They move them out of that geosynchronous order before they run out of fuel.
If they're responsible.
They had a sunspot that destroyed, I want to say, G5.
There was several over the years, TV satellites have been destroyed by solar activity.
Yeah,
That's right.
and that one just went.
Wanders.
It did.
Yes. Well, watch this. This is both hemispheres of Earth split into two. All the orange ones used to be on that nice neat line, but once their fuel ran out, they could no longer maintain their positions. And what's kind of neat is what perturbs them is actually Earth's moon. I think that's cool. Once they have no more fuel, they can no longer maintain their position, and so they start to wander. And by the way, this is a very serious problem. Notice, I find this one amusing. This one green one way over here, it just zoomed off the screen. Yeah, see that? Somehow that one's still active, even though it's out of fuel, obviously. That shows that whatever it does doesn't require very high precision with its communications. But the precision is very important with these. So those of you, remember C-band? Remember the giant dishes? Remember you could move them? You'd move that dish along that arc.
That's right.
Obviously, if the satellite wandered off, it would be a problem for your dish. You can't go outside and be like, I must see this ball game.
What I maintain,
What is that?
what I maintain is we're all being cooked.
Cooked?
Satellites, when they first went up 30 years ago, were less than 5 watts.
Yeah.
The DBS ones are 110 watts.
Yeah, but they're 110 watts at 26,000 miles up.
So what? You went from a 10-meter dish down to a 12-meter dish, a 12-inch.
Well, the reason the dishes, no, that's not because of power. I used to install satellite systems. So the reason the dishes are smaller is because in digital, you can over-amplify the signal thousands of times without losing a useful signal. Whereas analog, you have to have a giant dish because the noise gets so high if you try to over-amplify.
I understand that.
But even though we're being bombarded with signals from thousands of satellites, we're talking about microwatts because of the distance. They're 26,000 miles up. So and also there's something else. This is the same thing that protects us from cosmic rays, Earth's atmosphere. High energy cosmic rays do not penetrate down to the ground because of Earth's atmosphere. And the same is true of human satellites, although in the case of satellites this is a problem because that weakens the signal. And have you ever been up to Alaska and noticed satellite dishes? They tend to be bigger in Alaska because because they have to point very low, so they're looking through a lot more atmosphere. But if you're in Texas, you'll notice the dishes are small and also pointing almost straight up because they're closer to the equator. They don't have to look through as much air either, so that's kind of a neat thing. So,
And that's a hypothesis, and that is
Hypothesis.
longer on a triangle,
right,
so it's longer.
right.
Your distance between receive sites is.
That's also true,
substantially-
because you're near the top of the Earth, you're a little bit farther, but it's not so much the distance that causes the problem, but the amount of air between you and outer space. And I want to repeat, how many of you notice the stars twinkle more on the horizon? Have you ever noticed that? Twinkling is not real, is it? Twinkling is caused by Earth's atmosphere, so when stars are very low, they twinkle a lot, and when they're high, they twinkle very little, because you're looking through more or less air, respectively. And by the way, I'm going to end the show on this. Air is our enemy. As much as we like breathing, the enemy of astronomy is Earth's atmosphere. Which is why we tend to build observatories where?
Hi.
High up, dry, that's good, away from humans, and then ideally space, but that's very expensive. But if you can't afford a space telescope, Earth will suffice as long as you go as high as you can.
Go to Hawaii.
Yeah, now specifically not just Hawaii, but up on the volcanoes there. That's what, and do you know why Hawaii is good in addition to the height? Because they're surrounded by ocean. You have this huge smooth surface, and so the air is less turbulent. Turbulence is also a problem. That's why I hate to say it because we have an observatory here. The seeing conditions are not ideal here because we have the gorge, and we have mountains. The air is complicated here in Goldendale. Notice that. And you'll have nights with extremely beautiful, perfect seeing, and you'll have nights where it's a mess. We've had nights where we look at Saturn through the big telescope, and it looks like you can't even tell it's a Saturn. It looks like an oval. And then you'll have nights where it looks like a photograph. And that's all because of the enemy, which is again what? Earth's air. Yes, that's right. Well, you guys have been great. I hope you had fun. Thank you. And if you want to see more stuff, go to our website, GoldendaleObservatory.com. We have all the information about our limited Stonehenge operations, and they will also find updates on the new building.